Here's number density. This is molecules per cubic centimeter. So here I have NX, and again, it could be X, it could be I, it could be Bob, it doesn't matter. And this is the number of molecules of X per unit volume of air. It's a proper measure for reaction rates and optical properties of the atmosphere. So when we talk about ozone, and in particular we're talking about ozone columns measured from satellites, from space-based satellites, the way that that is determined is with this integral. So the limits of integration on this integral are 0 to infinity. That's not quite right. A satellite would see from the 0 would technically be Earth's surface, and then the infinity would be the satellite surface, or more specifically, the sensor surface on the satellites. And X would be the number of molecules of species X, and we would integrate that over altitude, or Z. And so we use this description for concentration when we want to measure absorption of radiation by the atmosphere. And we can relate this number density back to the concentration I described earlier through the ideal gas law, where NX equals the concentration from before times air density. And we can also define a mass concentration this way just by using density of the species we're talking about. So if we have the number of molecules and we know the molecular weight, it's pretty easy to go back and forth. And so the number density can be converted to mass density in a pretty straightforward fashion. And so we're not going to get too into the weeds on this, but this is how ozone is measured from satellites. And when the ozone concentration is given, it's given in terms of Dobson units. And so a Dobson unit is 0.01 or 10 to the negative 2 millimeters of ozone at STP, standard temperature and pressure. And that translates to 2.69 times 10 to the 16 molecules per centimeter squared. And you see how it's not per centimeter cubed, it's per centimeter squared. And this thickness of the ozone layer is measured as a column concentration, and that's why it's given per square area, not per cubic volume. A final way that we can describe concentration of gas phase species in the atmosphere is with Dalton's law and understanding partial pressure. And this is the proper way to describe concentrations when we're talking about phase change. And even meteorologists like phase change when you're talking about water vapor and the formation of cloud droplets. So here you could imagine the atmosphere, I told you a few slides ago, is mostly nitrogen and oxygen, right? It's and the pressure that the atmosphere has is primarily drives from the pressure of those two individual diatomic gases. And that total pressure is the sum of the individual pressures due to oxygen and due to nitrogen. So you could imagine if you had a plate filled with water and you're in Southern California and you put it outside on a hot day in August, you will come back later in the day and that water will have evaporated. And that's what would happen on a plain plate with no lid. But if you were to put a lid on that, eventually the molecules that were escaping from the condensed phase would collide on the lid and then return to the surface. And when the escaping flux rate equals the returning flux rate, that's when you have saturation. And that's a saturation vapor pressure. So cloud formation in the atmosphere requires that the partial pressure due to water is greater than the saturation vapor pressure of water. And the saturation vapor pressure of water and of most compounds is a function of temperature. And so we typically describe that with the Clausius-Clapeyron equation. And what I'm showing you here is that equation solved for water. A, B are given, and TO is a reference temperature, 273 Kelvin. And what I want you to understand is that vapor pressure increases sharply with temperature due to large latent heat. So if you want to get cloud formation, the higher the temperature, in some ways, the harder that's going to be. So I'm showing here the phase diagram for water. The x-axis is temperature in degrees Celsius, and the y-axis is the water vapor pressure in hectopascals. I used to be a professor at Rutgers, and I taught atmospheric chemistry in the winter. And so this was a really great way to help students understand this concept. I would look up what the dew point temperature was that day, and then I would show them, okay, breathe out. And so maybe your body temperature is about 40 degrees Celsius, I hope. And then when you breathe that water in your air, when you respire, when you breathe that out, it eventually cools down. And then when you can see your breath on cold mornings, this is why. So you breathe out the air at a certain water vapor pressure, it's at a certain temperature, it interacts with the cold air around it, the temperature drops, and you start to get condensed phase liquid water, and that's when you can see it. And the dew point, when you see that on your weather app on your phone, that's the temperature such that the vapor pressure of water is equal to the saturation vapor pressure. And it's this way to understand how temperature is in the atmosphere and how it feels to us. Sometimes you'll hear the meteorologist on TV or in your favorite app say, this is a temperature and it feels like this. And what they're doing is they're accounting for things like dew point or wet bulb temperature. And we're not going to have time to get into that. But just so you have an idea of where it comes from, and it comes from this very fundamental chemical principle. So I want to expand on this idea a little bit to understand why there was a runaway greenhouse effect on Venus. So in the class, we talked about why climate change happens, and it happens due to the trapping of long-wave radiation. So carbon dioxide and water vapor in the atmosphere trap outgoing radiation. And what happened on Venus is there was an accumulation of water vapor from the volcanic outgassing early in its history. The same exact thing happened on Earth. The early Earth was very, very dramatic, and volcanoes were constantly going off, and there was a lot of outgassing. But we did not get a runaway greenhouse effect on Venus, and it's because Earth is a little bit farther from the sun. And as water accumulated, it reached the saturation and it precipitated out, first forming clouds and then precipitating to form the oceans. So it's that same phase diagram from the slide before. And on the x-axis, you can see the temperature of Earth and where we're starting out at, and the temperature of Venus and where Venus is starting out at. And as the temperature rose on Earth, and there was lots of water vapor in Earth's early atmosphere, it eventually hit the liquid line on this phase diagram. Cloud droplets formed, they precipitated, and the ocean formed. Venus is much hotter, and as its temperature, as its water vapor pressure, or its mixing ratio even, started to rise, it never was able to hit the liquid line. And so the water vapor remains in the gas phase and continues to trap outgoing radiation. And this is why there's a runaway greenhouse effect on Venus. And the same thing is starting to happen on Earth now. The two products of complete combustion are carbon dioxide and water. We're primarily concerned with carbon dioxide. But if you hear someone say, oh, water absorbs radiation, that's also true.